Hello chemistry students, this is Dr. Tullis. We are moving on in our General Chemistry 2 class to look at the chemistry of acids and bases. In section 1 we are looking at acids and bases and how they are the most common substances in nature. Amino acids are building blocks of proteins. The information in your cells is DNA, which is deoxyribonucleic acid. The pH of lakes, rivers, and oceans, they're all affected by dissolved acids and bases, and many bodily functions depend on acids and bases. If you think back to Gen Chem 1, way back, you were introduced to two definitions of acids and bases, the Arrhenius and the Brønsted-Lowry definition. Let's look back at those two. An Arrhenius acid was a substance that, when dissolved in water, increased the concentration of hydrogen ions, or H+ ions. An Arrhenius base was a substance that increases the concentration of hydroxide ions, or OH- ions, when dissolved in water. So ammonia, NH3, would not be an Arrhenius base because that's not increasing the hydroxide concentration. A Brønsted-Lowry acid is a proton donor. A Brønsted-Lowry base is a proton acceptor. So we have a little difference in our Arrhenius acids and bases and our Brønsted-Lowry acids and bases. Here's an example of our Arrhenius acid. If I have hydrochloric acid, when dissolved in water, we can see that it dissociates into our H+ ions and our Cl- ions. An Arrhenius base, for example, sodium hydroxide, when mixed with water, will dissociate into our Na+ ions and our OH- ions. So this is our base because it produces hydroxide ions, and this is our acid because it produces hydrogen ions. We are going to really dig in and look at Brønsted-Lowry acids and bases though. Our general equation here is I have HA, so this is my acid, and we know acids start with H, hydrogen. Dissolved in our water, our H2O, it's going to be a proton donor. So our acids will donate this hydrogen. Hydrogen is a proton. It's going to donate it, leaving me with A-, because HA is H+ and A- combined together to make HA. But when that H is donated, then I'm left with A-, and that H2O just gained that H+ to become H3O with a positive charge. Now we know that because this is our acid, we know that because it starts with H, so that's our acid. That means that water in this case is acting as a base. The acid is a proton donor. We also can tell that because if I look at the right side of the equation to find the species that's closest to HA, H3O+ is not like HA, but OA-, the only difference between HA and A- is an H. The only difference between H2O and H3O is an H. So we have two pairs that have formed. One of them is always the acid and one of them is always the base in those pairs. So the question to figure out who's who is who has more H's. The one with more H's is the acid. So on the left, notice I have HA, that has more H's than just A. So this is my acid. H2O versus H3O. The one that has more H's is my H3O. So that is my acid. Therefore, the others are the bases. Base, base. So our acids are the proton donors, so they donate a hydrogen. Our bases are the proton acceptors, they accept a hydrogen. Now notice that on the right side of the arrows, in front of my acid, it says conjugate acid. In front of the base, it says conjugate base. That just means it's the pair to the original acid and base on the left. So my reactants are always labeled acid and base. The products, or the guys on the right, are the conjugate acids and bases. So if the HA is my acid, then the A- is the conjugate base. It's the base paired with the original acid. And my H2O is the base, so the H3O is the conjugate acid. Let's look at this example. I've got HCl plus water to give H3O and Cl. So to find my pairs most similar, I've got HCl and Cl. The only difference is that the left side has an additional hydrogen. So therefore the one on the left is my acid we'll call it A1. And on the right is its base pair, so B base, and we'll call it B1, or the conjugate base. I'm going to put a C in front of that. And then here I have H2O and H3O. The one that has the additional H's is going to be the acids, and the base, H2O, is on the left. The acid and the base are on the left. The conjugate acid and the conjugate bases are on the right. Let's look at another example here. I have HCO3 minus and water. Now these I already have the labels, but I'm going to show you how to figure out which is which. And on the right I have OH minus and H2CO3. Let's find the two species that are most similar on either side of the equation. First thing I notice is H2O and OH. The only difference between H2O and OH is one hydrogen. And the left side has the extra hydrogen, so the water in this case is acting as the acid. So on the right, the OH must be the conjugate base. So I have HCO3 minus and H2CO3. The right side has more H's, so the right side is the acid, or the conjugate acid since it's on the right, meaning that its pair on the left has got to be the base. Notice that each side has an acid and a base. We can't have two acids giving me a conjugate base and a conjugate acid. Once I looked at H2O and OH, and I went, oh, the left side H2O is the acid, I could immediately label the other guy the base. But I do like to double check and make sure when I look at the conjugate pairs that there is one hydrogen difference. Some molecules, like water, can act as an acid or a base. Notice that in this example, my water was a base because its conjugate on the other side was H3O. So the one with more hydrogens over here was the acid, and therefore H2O was the base. Notice in this example, my H2O was the acid because its conjugate on the other side was OH. So the one that had more H's was the H2O. If a species or a molecule can act as either an acid or a base, it's called amphiprotic or amphiprotic, either or. That just means it can be an acid or a base. So we need to look at its pair on the other side to see how it is labeled. Or you can look at the other reactant that it's next to figure out, well, if it's a base, then the water has got to be the acid. We have 5 different reactions here. Every reaction between a Brønsted acid and a Brønsted base involves 2 conjugate acid-base pairs. Remember that proton donors may be cations, anions, or molecular compounds. Proton acceptors might be molecular compounds, cations, or anions. So take a minute and see if you can label. Let's just look at this first one. I like to start with my water, and then I look at the right side and I have H3O+. The one that has more hydrogens is on the right, therefore that is my acid, and the one on the left is my base. Because it's on the right, it is the conjugate acid. And then I have HNO3 versus NO3. The one on the left has more H's, so that's my acid. I could also look and go, oh, well, my water was base, so this has to be my acid. Therefore, its pair, NO3, has got to be the conjugate base. Let's look at this next example. Here I have NH4, and on the right side there's an NH3. So that would be a conjugate acid-base pair. Who's the acid? NH4 would be the acid because there's more hydrogens. So that's the acid. This would be my conjugate base. And then I have H2O and H3O. This is my acid. I could automatically look at this and say that's my base, but I want to double check. H2O versus H3O+, H3O has more hydrogen, so that would be the conjugate acid. HCO3 minus and CO3 minus 2, the difference is one hydrogen missing. This would be my acid, this would be the conjugate base. H2O and H3O+, this would be the acid, and it's on the right, so the conjugate acid, this would be the base. Take a minute and see if you can label the last two. Here I've got NH3 and NH4. So NH3 is going to be my base, and NH4 would be the acid, or the conjugate acid. And then I have water, in this case, acting as the acid. All of the waters up here were acting as a base, but down here I have water acting as the acid. H2O versus the OH. H2O has more hydrogens, therefore it's the acid. And finally, CO3 versus HCO3. The right side has more H's, therefore it's the acid. H2O is the acid. OH is the conjugate base. Now we've been saying that one side has more H's than the other, but when we talk about being a proton donor, notice that I have labeled. I have HCl and Cl minus, so I labeled HCl as the acid, and I labeled the Cl minus as the conjugate base. And we labeled H2O as the base and the H3O as the conjugate acid. But what is happening here? As a proton donor, the acid is going to donate that hydrogen to the base because the base is the proton acceptor. So HCl, the H is going to leave it and donate to the H2O, which is why it becomes the H3O plus 1 charge, because a hydrogen, when the H separates from the Cl, it separates into a H plus and a Cl minus. And that H plus is going to then join up with H2O to not only just become H3O, but it's going to go from a neutral to a plus 1 charge. When I look at this example on the right, my acid, my water, we know it's the acid because its conjugate over here is the OH, which is one less hydrogen. So this is my acid, meaning that this is the base, and we double checked that because HCO3 minus versus H2CO3, this has got to be the acid. The acid, that's the proton donor, so one of those H's, and we can imagine H2O as being HOH. That's two H's and an O. One of those H's is going to donate its proton, donate its hydrogen to the base. Remember, the base is going to accept it. So it's going to go from HCO3 minus to H2, because it's going to grab that second H there, CO3, and it went from a negative 1 charge to be neutral because that H plus and that minus will cancel each other out. A negative 1 and a positive 1 will make it a neutral compound. So the acid is the proton donor, the base is the proton acceptor. Every single one of these examples will show that the acid donates the proton. In this case, the HNO3 donated that hydrogen to the base, which in this case was the water. So over here, the H2O became the H3O plus, leaving NO3 without that H is an NO3 negative 1 charge. Pause the video here and identify the acid, the base, and their conjugate pairs. Let's see how you did. H2PO4, and I've got HCO3. So I'm going to find the pair that goes closest with the H2PO4. I'm going to look over on the right-hand side for something with a PO4, and that, oh, right here. Now, what's the difference? H2PO4 and HPO4. The left side has more H's. That's got to be my acid. So the right side is going to be the conjugate base. Therefore, the other two must be partners, but let's just double check. HCO3 minus and H2CO3. This has more H's. It's got to be the conjugate acid, which makes sense because if this was the base, this guy has to be the acid. And if this was the acid, this has to be the base. Let's double check to make sure that we have that proton donor and proton acceptor. The acid, the H2PO4, is going to take one of those H's and donate it to the base. So going from H2 to just H on the right, it had a negative 1 charge, but because it lost a positive, it's going to now have a negative 2 charge on the right. And this HCO3 just gained an H to become H2CO3. It had a negative 1 charge, but because it gained that extra hydrogen, that negative 1 and a positive 1 gives it a neutral charge. Everything aligns. Check to make sure you got the second one and the third one to match. Acids like hydrofluoric acid, hydrochloric acid, nitric acid, and acetic acid are all capable of donating one proton. So they're called monoprotic acids because they have one hydrogen to give. HF has one hydrogen, HCl has one, HNO3 has one, acetic acid has one Those don't count. Other acids are called polyprotic acids, and they're capable of donating 2 or more protons. Let's look at phosphoric acid, for example. Phosphoric acid is a very familiar example of a polyprotic acid, and it can undergo 3 ionization reactions in water. Phosphoric acid combines when we have a hydrogen, obviously, and phosphate, PO4. And PO4 is a -3 charge. So to make this a neutral compound, if hydrogen's +1 and that's -3, it's going to be H3PO4. That means it has 3 hydrogens that it can donate, but it can't do it all at once. It has to do it 3 different times. And here's how it works. If I have H3PO4 with water, and it donates 1 proton, so I go from H3PO4 to H2PO4. This is my acid. This would be my base in that case. H3O would be the conjugate pair for water. Therefore, H3PO4's conjugate base would be H2PO4, and because I lost a proton, it'd be a -1. Then I can take that H2PO4 over here and donate another hydrogen to water. H2PO4 then over here can become HPO4 because it donated one of those H's. So H2PO4 minus then will become HPO4 with a 2- charge. Then I can take that guy and I can do it one more time. HPO4 only has 1 hydrogen left to give. If it donates to water, it's going to leave me with PO4 with a -3 charge, which is just phosphate. Here's a table with some polyprotic acids and bases. Poly meaning there's more than 1 hydrogen to donate. Because obviously if I have HF and I donate one of those hydrogens, my only option in base form would be F-. So this would be my acid, this would be my base. There's no in-between or amphiprotic form. I can have acid or base when there's only 1. But if there's 2 or more hydrogens, then I can have this in-between, this amphiprotic form. For example, H2S, hydrosulfuric acid, or we can call it hydrogen sulfide, when it donates 1 proton, so H2S, if I donate 1 proton, it's going to leave me with HS- and H3O+. But then, just like I did up here, I can take HS- and do one more reaction where it donates an H, leaving me with S2-. So the in-between form is that HS-, or the hydrogen sulfide ion. That's called amphiprotic. I could either donate a proton or I could accept a proton. If I donated a proton, I would go to my base form. If I accepted a proton, I would go to the acid form. In H3PO4, just like that example, I can donate a proton. H3PO4 cannot accept any more protons, but it can donate 1 or 2, and these guys can then donate 1 more and become a base, or they can accept 1 or 2 more to become the acid. Same with carbonic acid. This has 2 hydrogens it could donate. It could donate 1 to become HCO3-. It could donate a second one to become CO3-2-. Now HCO3- could give 1 more to become a base, or it could accept 1 to become the acid. Same with oxalic acid. Here I have 2 H's. If it donated 1, it would become this guy. If I donated a second, it'd become this guy. We could also take this amphiprotic form and we could accept 1. All of these guys could act as an acid or a base. I have 4 practice problems. What is the conjugate base of the formic acid, HCO2H? If this is acid, we want to know the conjugate base. So on the other side of the equation, that means it's going to have 1 less hydrogen. Doesn't matter which hydrogen we take. Let's say that we took this one, got rid of it. So I'm going to be left with the conjugate base of HCO2. I was neutral here, but I lost a positive. So I am now HCO2-. How about this? What's the conjugate acid of H2PO4-? Pause here. If we're looking for the conjugate acid, that means that this is a base. So we need one more hydrogen. That would be H3PO4. I was negative, but because an extra hydrogen brings about a positive charge, it's just going to be neutral at this point. How about the conjugate base for HCO3-? Pause. If we're looking for the conjugate base, this must be the acid. So I would donate that hydrogen, leaving me with CO3. It was a negative charge, but I'm losing a proton, so it's got to be CO3 2-. And lastly, which of the following is not an acid-base conjugate pair? HClO, if I were to lose an H, that would leave me with ClO-, not just Cl-. So this has got to be it. Let's double check and make sure. HF and F-, yep. HNO2 and NO2-, yes. The only difference is losing that hydrogen. And this should be H2CO3 versus HCO3. This is neutral and that's minus. That would work.